If you've ever stared at a geometry problem and felt like, wow, this is literally a completely different language, well, trust me, you are definitely not alone. Let's dive right into this explainer and decode Cambridge IGCSE vectors from the ground up. Today, we're going to treat vectors exactly how they should be treated, not as some super confusing abstract algebra, but just a simple, movable building blocks. And as you'll see by the end of this, these fundamental tools actually unlock incredibly complex geometric puzzles. Let's get started. Here is our game plan for today. We'll start with vector notation, move into multiplying by a scalar, check out measuring magnitude, and then pull it all together with vector geometry. All right, jumping right into section 1, vector notation. So unlike a regular number, which really just tells you how much of something you have, a vector gives us explicit instructions for movement. Think of it kind of like a set of really precise marching orders. When we write it as a column vector, that top number, the x, tells us our horizontal movement, how far left or right we need to go. And that bottom number, the y, well, that dictates our vertical movement, how far up or down we go. It's this neat, complete package of magnitude, which is the distance, and direction, just stacked right there in a column. Moving on to section 2, multiplying by a scalar. Okay, here's where it gets pretty cool. We can actually manipulate that basic movement using what we call a scalar. And a scalar is really just a regular number that scales our vector. So let's say we start with a base vector a that tells us to move -2 horizontally and 4 vertically. What happens if we multiply it by a scalar of 2? Well, we just multiply both the top and the bottom numbers. -2 becomes -4, and 4 becomes 8. We've essentially just drawn a line pointing in the exact same direction, but we've completely doubled its length. And the exact same logic applies if we multiply by, say, a half. We just have the components, shrinking the vector down while keeping its original heading perfectly intact. Now, here's an absolutely crucial point, the rule of opposites. What happens if our scalar is a negative number, like specifically a -1? Applying a negative sign to a vector is basically pulling a complete U-turn. If your vector a points forward and to the right, vector -a points backward and to the left. It reverses the direction perfectly, but, and this is key, it keeps the physical length exactly the same. Keep this little trick in your back pocket because it is going to be a massive help when we start navigating around actual shapes later on. Let's slide right into section 3, measuring magnitude. So magnitude, it sounds complex, but it's really just the formal math term for the size or the physical length of a vector. Obviously, the longer the length, the greater the magnitude. In our math notation, we show this by placing the vector inside these straight vertical bars, kind of like absolute value bars around the letter A. But how do we actually calculate that physical length when all we have is a stacked column vector? Well, we bring in a very old friend of ours, Pythagoras' theorem. Finding that length is not magic at all. It's a super straightforward 3-step procedure. Think about it. Because the horizontal and vertical movements of a column vector naturally create a right-angled triangle, the vector itself is literally just the hypotenuse. So, step 1, take your horizontal movement and your vertical movement and square them both. Step 2, add those squared values together. And finally, step 3, just take the square root of that sum and boom, you have your final length. Let's look at vector A in the table here with components 3 and 4. We square them to get 9 and 16. Sum them up, and we get 25. The square root of 25 is exactly 5, so our magnitude is 5. Easy, right? But what if the horizontal component is a negative, like the -6 down there? Well, when we square that -6, the negative sign completely vanishes. A negative times a negative is a positive 36. Add that to 8 squared, which is 64, and we get a nice, neat 100. The square root of 100 gives us a positive magnitude of 10. And remember, because length is a physical distance, your magnitude is absolutely always going to be a positive number, even if you're traveling backward on the grid. All right, so we've scaled them up, we've flipped them around with negatives, and we've measured their lengths using Pythagoras. But that brings us to a really vital question. How do these free-floating arrows actually help us navigate structured geometric shapes, like parallelograms or hexagons? Which perfectly tees up Section 4, Vector Geometry. This quote on the screen, this is the ultimate secret to unlocking vector geometry. Vectors are not fixed in position. See, unlike coordinates on a graph that are stubbornly pinned to one specific spot, vectors are totally independent. An arrow pointing 2 units right and 1 unit up is the exact same arrow whether you draw it at the top of the page, the bottom of the page, or if it's forming the side of a shape. They can slide absolutely anywhere on a page just as long as they don't twist, rotate, or shrink. Let's break down exactly why that's such a game changer. Because vectors act as these movable templates of movement, any two parallel lines of the exact same length that point in the exact same direction are mathematically identical. And this gives us the incredible superpower of substitution. If you figure out the vector for the bottom of a parallelogram, guess what? You automatically know the vector for the top. It's the exact same vector. And remember our rule about negative scalars earlier? If we need to travel down a side of a shape but we only have the vector pointing up, no problem. We just slap a negative sign on it and we can retrace our path backward perfectly. Take a look at this table. You can see just how easily we translate physical shapes into simple algebra. If a shape has equal parallel sides, like side BC and side AD, we just write BC equals AD. They are the exact same vector. What if we have a diagonal line that is perfectly parallel to another line, but it's exactly twice as long? Well, a line BD that is twice as long as BE is just written as 2BE. And if we need to describe a line running backwards along a known path AB, it's simply minus AB. Suddenly, solving a massive, complex shape isn't about using a protractor and measuring angles, it's literally just substituting simple algebra. It really shifts your perspective, doesn't it? As we wrap up this explainer, I want to leave you with this thought. If mastering one simple repeating column vector is enough to unlock all the complicated pathways of geometric shapes, what other seemingly impossible mathematical mysteries are actually just built on simple repeating patterns waiting for you to decode them? Keep your eyes peeled for the templates, and I promise the complex becomes remarkably simple. Thanks so much for exploring this with me today.